dynamics of terrestrial ecosystems using different lidar remote sensing platforms. He is currently working on NASA's Global Ecosystem Dynamics Investigation mission. He is on the science definition team. And Dr. Tang is a recipient of NASA Earth and Space Science Fellowship and NASA New Investigator Award. Okay, I will give the floor to Dr. Tang.
Thanks for having me. So just give us kind of a really brief introduction here, since GEDI, what do we call GEDI a lot of times, been mentioned several times. So this is actually where GEDI is going to be spotted on the International Space Station. So this is part of the International Space Station, the Japanese experimental module, the JME-EF, and that's where we're going to have GEDI. I believe we're going to have the eco-stress there pretty soon as well. Oh, it's already there. That's the reason why we're not usually pointing to the continent US and pointing to Japan instead. Anyhow, just a little bit of background story, and this is the title of my talk today: Mapping Global Canopy Cover in a Vertical Profile Matrix using Spaceborne lidar. So to begin, I know a lot of people here doing lidar work as well. For example, John, he was saying he was using a lidar to see the same atmospheric profile or aerosol, the other things. But we can use lidar to do the 3D vegetation structure as well. A little bit outline here. So why we need lidar to do the 3D vegetation structure, and how we actually measure the vegetation structure, how accurate are these measurements. And of course, there'll be a bunch of applications of the 3D vegetation structure. And of course, I'm going to share in the part 2 of this talk, that's about the latest development of GEDI, which is due to launch within a month. So vegetation structure, what are we really talking about of vegetation structure? This retrospect of the past centuries development of climate models. Initially, it's just atmosphere and the ocean. And then we have land there, more realistic geography, changes of clouds. And it's not until in the 2000s we have the concept of dynamics of vegetation. So what do we do with that? One component of this is the land cover or forest cover change, for example. This is from the Dr. Matt Hansen in our department as well, using the Landsat data to characterize the forest gain and loss at 30-meter resolution. But this is only one part of the story. We know forests can be clear cut, so within this entire parcel, for example, somewhere in the Amazon, it's all gone. But it might also experience some kind of the degradation at final scale. And that's more related to this concept here, the Pullman-Monteith leaf. So we can use this fine-scale vegetation model to describe a bunch of the physiological and physical processes. A simple way to process or to approximate this process is using a concept of leaf area index, which describes one amount of leaf or foliages within the forest, notably. So this is an example from the Modis LAI product. And you can see pretty much over the entire Amazon, it's so-called dense forest with a value of about 6, if I could say so. So that raises the question. So is this really a good idea how we capture the vegetation dynamics or structure? Probably not. Why? So first of all, let's go to the definition of forest structure. LAI is a really good description of forest structure, but not good enough because the forest structure refers to both the horizontal and the vertical distribution of the ecosystem elements and their interactions. This is what we usually would look like when you walk into a tropical rainforest. We have really tall immature trees that can grow more than 50 meters. Below there, at about 30 meters, we have a nice thick blanket of canopy layers that can intercept 90% or more of the solar radiation. That means it usually creates limited radiation conditions for this outer canopy and the shrub layers. And based on this structure, we have important functions. Notably, I just mentioned the light interception, and it in turn to help the forest to grow. So that's all we know as photosynthesis. And it can be more complicated. So in the tropic forest, notably, forests can change over time, known as the events of the evolution or the disturbance cycles. So we have pioneer trees that can grow usually pretty fast. Most of them like kind of the shade intolerance or like enjoy the sun most of the time. And as it develops, it created an environment called like vertical diversity. So it creates an environment that allows some kind of small trees or shade tolerant trees to grow below this tree. And when it reaches maturation, it's a more complex story here. As I say, like it's really complicated and changes over time. People might ask, so why do we care? Why couldn't the LAI just kill all the things off? So here's the reason. For all the important functions, I will just name 2 of them. The first one is biodiversity. So biodiversity matters because we're losing it rapidly. Here's an example in the Amazon forest. All the reddish and brown color indicates the presence of the endangered species. So it's pretty high over this area, which is kind of our common knowledge, usually across the roads or the disturbed forest. But check out all these green areas, this green intact forest. It does not necessarily mean there's no endangered species there. It's just because we don't have enough knowledge about this forest. So what do? One good solution is to link certain forest metrics with the biodiversity information there. And it turns out to be like the forest structure matters a lot. And here's an example in the Habitable forest. Scott Guest did some early work on that. You see a nice laxated wobbler thing at the branch, but that's actually where it's not staying most of the time. In fact, these birds prefer have their nests at the understory layer. And here's the female and the little ones. This study really echoes the classical study done by MacArthur in the 1970s, saying that the vertical stratification of forests really matters in the biodiversity studies. And if we have a better quantification of vertical structure globally, that can really help us target our conservation efforts and mitigate losses in rapidly changing areas and focus our limited resources just over the hotspot areas. Number 2, carbon cycle. Well, I guess a lot of people here dealing with the carbon a lot. So right now we have a large uncertainty in our carbon budget, not only in the total stock, but also in flux. And this is what we see here. As trees grow over time, usually it takes a lot of carbon sink, especially in the early stages. And right now we're not like that sure about the stock in the primary forest, and we don't even know whether they are carbon sink or carbon source because it's subject to the climate change and other different factors. But we do know this for sure, like a major carbon sink. And one way to capture like how much carbon got absorbed by the forest is using, for example, the lidar index and all the like light efficiency models. But we have a problem here with all the LAI. That is notably in current observation we call the saturation effect. We know there is a nonlinear relationship between the famous NDVI and the LAI. Once when the LAI goes about 4 or ish, and like what makes things more complicated is for the young forest, saying like young secondary forest or a little bit older secondary forest, the LAI can get pretty high at the early stage. Around like 10 to 15 years, it already reaches 80% of the maximum. That really limits our current observation of the LAI and the capacity to absorb the carbon cycle. And this pretty much forms my kind of the basis for why we need a vertical stratification of more accurate LAI. So how we measure the vertical structure and how accurate are these measurements? This is my second question here. I approach this using the lidar. LiDAR is short for light detection and ranging. It's an active remote sensing method that uses the laser pulse to measure the distance to a target. In fact, LiDAR does not exactly measure distance. It only measures the timing. But we know it's a constant speed of light, so can easily get the distance correct. Here's a little animation made by NASA GEDI, but it's primarily used for give an introduction about the planetary uses of the laser, because in the previous time, people mostly used the lidar to measure the DEM, for example. It wasn't until the 1960s and 70s people realized the noises in the original lidar data turned out to be like important information about the forest. And after that, boom, everything exploded, and it's a huge amount of applications of using lidar to measure the tree height, above ground biomass, as well as leaf area index. Here's kind of a kind of classical example from Michael Levsky describing two types of the lidar. We have this here showing a waveform-like lidar, and also we have like this little plates here, a data example from discrete return lidar. I'm gonna introduce, before introducing the Spaceborne lidar, I would like to give a quick tour about the more widely used lidar tools, notably the terrestrial lidar and the airborne lidar. Terrestrial laser scanning, you will call it TLS. These are like ground lidar based, and you put it in the forest plot that it's scanned, it can really recreate the forest structure in high detail. These are the examples in the Sierra Nevada National Forest. You can see all the leaves in green, the barks in the yellow, and all the pinks of ground. And the image credit goes to Alan Strand and Chris Shelb in Boston University. So this is their cute instrument called Echidna. But that was really like more than 10 years ago. In these days, like the TLS developed so fast that there are a bunch of like powerhouses in the commercial market that kick in. Notably, this data, for example, comes from the Rigo VZ400 scans in London, and some work done by Matt Disney. So we can identify individual tree crowns here, a sycamore and an ash. And there'll be a lot of like data now, so people actually want to decimate the data a little bit, so it can be easily plugged into the other models. Right now, it's really an active research field. Airborne lidar data. This is by far the most widely used data, especially in US, because we have a lot of the open data flown by the NEON or the other companies and the research groups here. I would like just give a brief introduction about the two classical examples of the lidar data I just mentioned: the discrete return lidar data and the discrete return lidar data. That's more widely used, and also a full digitized waveform. Basically, they describe the same thing, that is the interactions between the laser energy and all the elements it hits during the propagation process. So with this, you can have a brief idea how the 3D structure elements distributed in space. For example, with full waveform lidar, we can have this kind of the famous green form in our lidar acronym. So you can see a bunch of like the leaves within this waveform. And when you have multiple paths and mosaic them together, you can recreate the 3D scene like this. And clearly, it has the advantage over all the traditional passive optical remote sensors you've seen. Like notably, on the first row, the forest cover percentage derived from NASA, from the GLCF, also at Maryland Global Land Cover Facility. The GLAS Manhattan data set, an LCD data set. This represents like Google Earth image clip here. You can clearly see like lidar has the better visualization capacity with all of them, and like all the shadow problems or all this kind of uncertainties related to the height distribution can be all resolved by lidar. And these are the two other aggregated results from the waveform lidar and the discrete return lidar. So in the end, like can deliver a better message about not only the height but also the cover. And based on the cover, we come up with the idea of deriving the vertical AOI profile. It's quite simple. Like in general, it just follows the Beer's law to give us the idea of how light attenuates within the forest canopy. What makes the lidar quite useful is because it's simple and quite accurate. It follows all the physical laws, and that's how we like build our house based on this foundation. And here's my favorite spot in the Civil Biological Station, Central America. All the red dots represent like each individual measurements of this tower. So what actual people do there, just build the tower, and the field crew members collect all the leaves and measure them in a lab to give you the best representation of the vertical forage distribution in the tropics. How would it compare with lidar? This is what it looks like. Pretty good, huh? Like there's no saturation effect even when the AOI goes to 10, and it follows the pattern excellently. And there's no bias when using the power measurement against the lidar measurement. And started from Scott Stark, another group from the Arizona, like pretty much the similar thing using the discrete return lidar, and it got similar results. So this really strengthened our confidence using the lidar to give the most realistic structure distribution. And now here we go, Spaceborne lidar. These are the examples from the ISet 1. Since we have quite a high confidence in the airborne lidar data, we think well it should apply to the Spaceborne lidar as well. So we took the ISet 1, the GLAS onboard on the ISet, and it is the full waveform lidar at the 1064 nanometer. It has the vertical sampling resolution of 1 nanosecond with a footprint size about 65 meters. So it scans like in transect. So what you will see is like individual footprints along the orbit. So it's about 170 along the track, and it has a really wide cross-track distance. Notably, in the at the equator, it's about 20 kilometers across. When I applied the same algorithm to ISet and compare it with airborne lidar data, well, you would expect somehow like I would call acceptable or medium agreement between these two, because there are always some kind of issues with ISet or with Spaceborne lidar compared with airborne measurement. But still, it really represents our best guess about what the actual forest structure is like. And we will see here, this like the overall accuracy for total AOI is the best. And as it goes down to the unknown story, the accuracy usually decreases because it's less direct measurement. It's more like based on the estimation. So there are being like a bunch of the vegetation variables based on the ISet 1 data. The canopy height, for example, from Mike Levsky and Mark Simard at JPL, and also above ground biomass estimates, notably Sasan Sachi and Alexander Bacchini. I'm more interested in this, the AOAI vertical distribution. So what you see here is the amount of the foliage by height interval over the Amazon forest. You will see here, for example, most of the peak of the foliage will be around 10 to 20 meters at the forest deforestation archive in the southeastern of the Amazon. And in the contrary, you will see like over the middle of the Amazon, most of the like foliage will be around like 30 to 40 meters. And now you have a comparison with the MODIS data. You see a clear difference here, right? So there's pretty much no variation over this area, but we can see a clear contrasting pattern, even though their total value pretty much being equal. Now, so with this new information about 3D, we're going to deal with them. So there's got to be something like cannot be simply reviewed by a total AOAI. And what is that? We've done a lot of tests, and here are just a bunch of examples. I imagine there will be more, but here are just 3 examples to highlight why it's important to use this vertical information. This is a more recent publication by the PhD in our group, Susanna Marsalis. What she does is essentially taking the AOAI profile, like it's pretty much the same 10-meter integration, mosaic them together, and she finds a really nice pattern here. So a pattern that cannot be seen from the total AOAI or total canopy cover. Pretty much you see no variation. Oh, by the way, this is in the low pay. It's in the low pay of Gabon. That's Central African rainforest there. So what you will see here is like over this particular area, you will see most of the foliage will be clumped over more than 30 meters in height. But here, in this kind of island here, you will observe like most of foliages be clumped at about 0 to 10 meters in height. It's a really contrasting pattern that can easily show up here in 2 different colors. And it turns out to be this forest here with most of foliage up in the canopy would be the monodominant, like a local forest, Ukume. And here it's actually the colonizing forest. So that's why it has most of foliage down on the ground. And we can easily make a prediction based on this profile and tell us what's the distribution of the, what's the vegetation context based on the vertical information. And again, recall this previous total AOAI cover, that's not give you anything. This is another application of AOAI profiles, some work done by Scott Stark, and using similar way, once you get the waveform and then know the area distribution, we can recreate the tree size distribution using certain constraints because we have a pretty good idea what a tree is supposed to look like, individual tree is supposed to look like at different stages. And you can unmix this to give you like the distribution or pretty much succession stages of this particular forest. This work is being done in the Amazon, 2 plots in the Amazon. And there certainly can be more of that. There's a bit of work I've been doing that can help, like called by the NS Decadal Survey, saying, well, it helps resolve the long-standing debates about the influence of drought on tropical forest productivity and variability. So this goes back to the original argument, whether Amazon forests green during the dry season. Like, there being kind of a couple of the communications on this topic. So what I did, just like I would love to see what actually the season means in the Amazon. When people argue about that dry season, most of the time they spend the time talking about the June or July to August in the central Amazon, which is only one tiny part here. But in fact, Amazon is big, and the seasonality there is really complicated. The dry season usually starts like pretty early in the southern part, like around March or April, and then the precipitation moves all the way to the dry season moves all the way to the north. So what you see here is like the start of the dry season, again, like around May-ish, like at the southern part, and then July or June in the center, and in the northern part, it won't dry up until later of the year, so November or December. And really creates a unique environment conditions because the duration and the amplitude of the drought, in fact, is going to be different. So when I lay out with the ISet observation with that, I see like, like the canopy part pretty much follows the track of the starting of the dry season. In a sense that when you have enough water in the soil at the start of the dry season, and you have increased radiation, that prompts the growth of the leaves, and that's why you see all the green here. But when you run into the second part of the long dry season, probably 6 months or longer in the southern Amazon, trees don't really stand that long. Like you started to defoliate a little bit. That's why it becomes the yellow part here. And then during the wet season, there are more complicated patterns. And this pattern replicates as the rain season or the dry season shifts spatially. So in a sense that the entire seasonality in Amazon is complicated because it changes not only temporally, but also spatially. And when you see that, you will see like the dry season appears at different times. But that's not the end of the story. So we know like trees have different layers. When the upper canopy is starting, for example, here in the southern Amazon, is starting losing foliage during the peak of the dry season, it opens up some gaps and allows more radiation reach down to the subcanopy layer and shrub layer. That gives you like extra radiation for all those kind of, mostly shade intolerant trees and the seedlings there. And most of this vegetation spend like almost their entire life in shade, and a little bit of increase will prompt their growth. So that's why they started growing during the peak of the dry season. So I believe putting all this together can really help like resolve our uncertainties about the productivity and the variability in the in the Amazon forest. That's kind of all the applications I'm going to show. I'm certainly envision there are going to be a lot more than this. That's why we need GEDI, because ISet, as I mentioned, is only really coarse resolution, like more than 20 kilometers cross track at the equator. But GEDI is better, way better than that. GEDI is the NASA Earth Venture instrument mission selected in 2014. AI is my PhD advisor, Rob Bio. It was cost capped at $94 million, and it's going to be launched in a month, hopefully. We're going to see how SpaceX is going to do its job, because the failure of the studies definitely have some kind of impact on this. And this is the overall goal of GEDI: advance our ability to calculate the effects of changing climate and land use on ecosystem structure and dynamics. Pretty much like this too echoes my previous example, why we care about the structure of the forest. And there are a bunch of key questions here we want to ask. What's the carbon balance of the Earth's forest, in terms of the current stocks, like forest biomass, and also the dynamics related to the disturbance in the recovery. And we'll also use models to see how much carbon is going to be sequestered through forest in the future. And we need the vertical information to help us quantify the relationship between the biodiversity and the forest structure as well. So in total, GEDI will probably make up to more than 10 billion shots over the forest and land areas. And it's supposed to run for a nominal of 2-year operation. The key measurements from GEDI is as simple as this: the waveform. This forms everything else based on the waveform or geolocated waveform, so we know where we are. We have the waveforms on each on all the landed area. The geolocation area of the GEDI footprint is expected to be around 8 to 10 meter, 1 sigma. It could be better after the post-processing being applied. And the key deliverables of GEDI are the level 4 product, which is the biomass, implicate at both footprint level as well as grid level. So the other L4 products, all the demonstrative products, including carbon change, Landsat, based on disturbance events, and other bunch of things, only be produced over selected areas, so not globally. And here's a table of all the data products above, the approximate resolution. So 25 resolution of geolocated waveform, and that includes all the other metrics, including the height of the forests, the ground elevation, and the canopy cover LAI, which I'm being responsible for delivering. And we're also going to grade all the level 2 products, making a 1 kilometer grade globally after the mission finished. Because this is a progressive process, we're not going to release the 1 kilometer grades after 6 months or a year, because it needs to collect more data to fill the gaps. And the level 4 biomass footprint and grid products, and there are a bunch more at various resolutions. So it's a little bit of spatial specifications of GEDI. So GEDI, again, it's a sampling waveform LiDAR. This is what you mostly would see from the airborne LiDAR acquisition. So imagine this is a 1 kilometer box. Airborne LiDAR will fill all the boxes in a wall-to-wall manner. And for GEDI, this is going to be only a bunch of the tracks. And of course, these are the field plots. And we also have the terrestrial LiDAR collections over certain areas. So together, they give us a really good representation of the forest structure. And again, this is what essentially GEDI is going to measure. So you have this attenuation of the radiation through the forest. And here we have the ground return. And based on all the GPS information, we can characterize where these footprints are and how accurate this can be highlighted. This is one orbital track from the International Space Station, and there'll be a bunch more of them. Sorry, I couldn't make it better. But all the green areas are actually covered by the orbits. And the red is just only one example. And for example, we can select to choose to target some of the large areas because GEDI has a pointing capacity of about 200 meters. We're still in a final plan for how we best leverage the pointing capacity and the area of the observation, the ground observations. And these are the spatial configurations of GEDI track. So along track, you will have about 60 meters in distance, and across track, there are 8 of them. It's going to be around 600 meters. So in total, a swath, in a comparable base, about 4 kilometer swath. These are the requirements of GEDI. We have a baseline requirements that's 80% of the 1 kilometer forest cells will have a biomass accuracy of 20% standard error, or less than 20 megaton per hectare. And we'll acquire transects of canopy profiles in conditions of up to 95 and 98 canopy cover. And we also have a threshold requirement which lowers the baseline requirements a little bit. And we're also going to record, validate, and push all the data through the NASA DAC. I believe the level 1, level 2 are going to be in Oak Ridge, and level 3 and level 4. Level 3 and level 4 are going to be on the LP DAC. I can verify this later, but it's a general idea. Here, I would like to focus a little bit more on the canopy covering and the AI profile, since I'm responsible for dealing with that. We have done our pre-launch testing in Africa. Like this is where like the previous exam come from. So NASA been flying not only the ELVIS, the airborne lidar protocol, and other like the SAR data over the Gabon in Central Africa. So you can see this pretty good coverage over this country. And this what you see here down here is a nice gradient between the savannas and the created during the last ice age, and the dense forest down in the south there. This is the initial comparison results. We have both ELVIS data as well as terrestrial lidar scans. And the black dots here represents the TLS scan points, and the red circles represents the ELVIS footprint size. So we can see a really nice relationship between these two. So pretty much no saturation at all, and you can see this relation stays almost the same through different height intervals. And I also calculate the algorithm-related uncertainty. Not surprisingly, as we go to final vertical resolution, you will expect somehow a larger uncertainty. But at saying a vertical resolution about 50 meter, about 5 meter or 10 meter, most of the algorithm uncertainty will be gone. So pretty much echo our validation results, saying there's a slight trade-off between the accuracy and the vertical resolution. So I think from the user's perspective, I would recommend a 5 meter resolution using GEDI data. Level 4 biomass calibration strategy, I will quickly go over this. Right now, we don't have any kind of real GEDI data. The way we're trying to build the GEDI biomass model is through simulated GEDI data. So we collect as many as field data and corresponding lidar data, simulated GEDI waveforms, and extract the certain corresponding GEDI metrics and build a model based on the simultaneous acquisition of lidar data and field data. And then we've already got our model set up. So once we get the real GEDI data, we just apply the model, and it gets the estimate and uncertainty. And this is how it goes for now. So we have a GEDI forest structure database. Oops. And we've already collected more than 4,000 plots global-wise, and this certainly gives us a pretty good representation of global forests, and still in progress. And we're expecting more help from the community. And for now, like pretty much going to a new era of the ecosystem observation, because we know there are going to be a bunch of them on the International Space Station as well. So I just mentioned like the EcoStrace, and we're also going to expect the OCO3 and HiSeal, like the hyperspectral one. So together, they give us a better representation of the terrestrial biosphere models, because we can have not only the structure, but also like that's the physical part, and also like the biochemical part. And it can really help the model forecast in the future. And it's only going to happen like pretty soon in the next few years. It's really exciting. And this is one of the, from one of the recent papers published on the Nature, Ecology, and Evolution. So it can highlight like all the instruments and centered on the carbon sink potential and the disturbance ecology. And this is very unique from GEDI. That's the height, volume, and the barrier index. Pretty much I'm going to be done here, so I'd be more than happy to take a bunch of questions. And may the forest be with you. That's our GEDI logo. Thank you.
Questions?
Yes. I believe so, but this is not going to be the focus of GEDI. Brian Bolano said that he will keep some part of that for analysis, but like again, it's going to be really coarse resolution for GEDI. We have limited capacity on ISet, so the short answer is it has the potential, but not required. I'm sorry. I see. It's going to be based on the existing data set, saying the SRTM data to see where the cloud trigger is. So it's pretty much the same way as ISet 1.
Similar question is that basically you have a lidar that will detect return with any signal on its pathway.
Right.
So that means cloud, aerosol, etc.
Yes.
They are themselves very valuable information.
Yes.
So any plan to generate a product of cloud or aerosol?
No, based on my knowledge, we are not going to generate any. We're not going to generate any of the data.
It's particularly useful for aerosol because
Yes,
aerosol is near surface, and your intention to get vegetation. That means the signal must be very strong, reach to that point.
Right.
And often like Calypso, designed for aerosol, but nevertheless, it's once to near surface boundary layer, the signal is really weak. So,
right.
So in that regard, it should be equally valuable for aerosol remote sensing.
Yes, based on what I know, that all the data is definitely going to be kept a record in the level 1, and probably like this part is going to go to the, level 0. It's going to be stored somewhere on the deck, but like probably it will be like, I don't know, independent certification for like beyond the GEDI. For us, we are only interested in the forest part, and what it gets for the level 1A products, I think it's about like only 100 or 200 meter stacks over the like intersect over the grounded area. Right. But I'm pretty sure like this data is going to be like information is definitely there, but it's definitely not ideal. Like the same way as ISet 1, it's not going to be like as good as ISet 1 in terms of that part. That's a good question. I mean, like, but now, like, we assume similar procedure following like the Elvis process. Mr. Hao Tang primarily responsible for this, and we've done a bunch of work dealing with kind of a similar data set. It turns out to work like pretty well. I wouldn't say 100 times, but 95% of time it's going to be a pretty good result there. And compared with ISet 1, ISet 1 is notably like difficult to extract in ground because it has such large footprint, and you won't expect a perfectly flat like over like 65 meters. But for GEDI, it's going to be like 20 to 25 meters. Slope has a less pronounced effect over a small, relatively smaller footprint. And but like you can't really tell until the until the data comes back to you.
So yeah. So it looks like the GEDI's primary data product is biomass, right? As you said, right?
Yes.
Are there any ancillary products other people can benefit from using the information to get at something like, I'm thinking about climate feedback. Mm-hmm. Things like surface heat flux and albedo, roughness, and things like that. Are there work within this project to be able to use that information to actually get a better estimate on the climate feedback problem? Yeah.
Like, I guess this goes beyond to the next solicitation or the like whatever from NASA, from NOAA, because GEDI is, as I showed, like we are kind of limited to budget. It's only 94 million. It's really small for a space mission.
But what I mean is, technologically, is it possible? I mean, is it that you could actually use that information, or obviously a lot of modeling involved in order to get at that with some data constraint? Yeah. Absolutely.
Like that's why I bring up like the whole area and a profile like here. I would believe GEDI will produce so far the best 3D structure globally and at 1 kilometer resolution. Right. Yeah. So I think that's going to be super helpful for all the modelers. Mm-hmm. Yeah. Or unless like you have some, it would be great if you come up with other ideas. Say, well, there's some bunch of other biophysical variables going to be input into your model. To me, like the most obvious one would be the canopy cover, the LAI, and the height, and the biomass as well. So.
Okay, so I think data is very good intermediate level between this spaceborne and airborne. And my question is, how long is the revisit time? I mean, just the ISS, how long it can cover the whole green area you plotted?
It's like a little hard. Like first of all, back to your first question, the revisiting time. GEDI does not really have the revisiting capacity. The current designs we sample as many different places as possible. So like revisiting is possible, but it's definitely not our priority. We want to cover like always a trade-off between like the temporal resolution and the spatial resolution somehow. For the second part, I believe Could you repeat your question again? Like, I'm sorry.
I think in your configuration in one of your slides,
yes.
You have lidar track. No,
Right.
How long can this can GEDI cover all the green areas?
I would it's hard to tell right now because all the cloud and aerosol gonna have the effect there. Pretty much we won't use any of this, like we call contaminated data, like in our forest observation. So probably it'd be better to wait for at least an year. Current plans that the GEDI run in a systematic sampling for at least 6 months to see what it really looks like first. Right. We certainly have that analysis, but it's just like I can tell you in a deterministic way, but it's not going to be that accurate to fill all the gaps. It's better to wait at least an year to see. It's quite different from satellites, sure. And it also depends what kind of resolution you would accept. Saying like to achieve our ultimate goal at 1 kilometer resolution, we need 2 years. But if we are okay with, say, 10 kilometer resolution in some of them, because some of the models I'd be happy with like half degree, that's 50 kilometers. You can easily meet that requirements in 6 months. So.
What's the accuracy on the elevation?
Accuracy on the elevation. This I can't really replicate what Scott Lusky gonna say, but
I saw 5 slides, but I wasn't sure what that was.
You mean? Oh, this one here. That's for the level 2. That's the LAI kind of the goal of delivering the LAI profile at 5 meter vertical resolution. So essentially, it's a profile. And we use it's a trade-off between the accuracy and the vertical resolution.
So if you have a stand of trees, canopy,
right.
how accurate can you measure the top of the trees?
Oh, that's pretty accurate.
With respect to some datum, yeah. What accuracy? Centimeters, meters?
It's about kind of 1 or 2 meters.
1 or 2 meters.
In terms of the height of the tree, yes.
I think that's it. Very impressive. Thanks.
Yeah.